God morgon och välkomna allesammans till Kungliga Vetenskapsakademin och den här presskonferensen. Vetenskapsakademin har avslutat sitt sammanträde och det är dags att presentera årets Nobelpris i fysik. Jag heter Göran K. Hansson och är numera akademins ständige sekreterare. Och med mig här framme har jag professor Anne Lullier som är ordförande i Nobelkommittén för fysik och professor Olga Botner, ledamot av Nobelkommittén och expert inom prisområdet. Welcome to the Royal Swedish Academy of Sciences. It's time to announce this year's Nobel Prize in Physics. I am Göran Hansson, Secretary General of the Academy, and with me on the podium is the chair of the Nobel Committee for Physics, Professor Anne Lullier, and Professor Olga Botner, member of the Nobel Committee. I will start by reading the announcement with a citation in the 5 languages Alfred Nobel spoke, and we will then hear presentations from our experts on the panel. After that, we hope to have one of the Nobel laureates available on a phone line, and we look forward to your questions, of course, in Swedish or in English. Årets pris handlar om identitetsbyten hos några av universums vanligaste invånare. This year's prize is about changes of identity among some of the most abundant inhabitants in the universe. Kungliga Vetenskapsakademin har beslutat att utdela 2015 års Nobelpris i fysik till Takaaki Kajita och Arthur B. McDonald för upptäckten av Neutrino Oscillationer som visar att neutriner har massa. The Royal Swedish Academy of Sciences has decided to award the 2015 Nobel Prize in Physics to Takaaki Kajita and Arthur B. McDonald for the discovery of neutrino oscillations, which shows that neutrinos have mass. Für die Entdeckung von Neutrino Oscillationen, wodurch bewiesen wird, dass Neutrinos Masse haben. Pour la découverte des oscillations de neutrinos qui montrent que les neutrinos ont une masse. Za открытие осцилляций нейтрино, что показывает, что у нейтрино есть масса. Thank you. And now, the chair of the Nobel Committee, Professor Lullier, will give us a brief introduction. Anne, please.
At this moment, in this room, there are more than 1 billion neutrinos, which travel almost at the speed of light. These elementary particles are the second most abundant in the universe, next to the photons, which are the particles of light. They are created in nuclear reactions, for example, in the sun, in stars, or in nuclear power plants. They interact very little with the environment. For example, they can go through Earth without being stopped. There are 3 kinds of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. This year's prize is awarded to the experiment discovery that neutrinos can change identity. For example, a muon neutrino can become a tau neutrino and vice versa. They oscillate. The observations were made by 2 research groups, one at the Super-Kamiokande Detector in Japan and the other at Sudbury Neutrino Observatory in Canada. The discovery implies that neutrinos, which were believed to be massless, do have a mass, even if very little. And since there are so many of them, it changes our view of the universe.
Thank you, Anne. Now, Professor Olga Botner will give us some insights into the science behind the prize. Olga, please.
I'll be happy to. Neutrinos are a puzzle, and this year's Nobel Prize in Physics honors a fundamental step towards unveiling the nature of the neutrino. As we just heard, neutrinos are very common fundamental particles. Many are created in the solar core. Others are created when cosmic rays collide with atoms in the atmosphere. Others still are created by decays of radioactive elements in the Earth's crust or in our nuclear reactors. Every second, billions of neutrinos pass through our bodies, unfelt and unseen. Neutrinos are nature's most elusive particles. They hardly ever interact. But sometimes a neutrino will strike an atom, and when it does, charged particles are produced, and those we can detect. And this is how we know that there are three kinds of neutrinos. We call them flavors, neutrino flavors. We have electron neutrinos. Those, when they interact, always produce the electrons. But we also have muon neutrinos and tau neutrinos, which, upon interaction, produce muons and tauons. And muons and tauons are heavier relatives of the electrons. They have properties just like the electrons, they're just heavier. And apart from that, this is about all we know about neutrinos. And for more than half a century, we used to think that neutrinos are massless. The discovery of neutrino oscillations at the turn of the millennium upset our notions. This discovery comes in two parts. The first part has to do with the neutrinos from the atmosphere, the atmospheric neutrinos, and the second part with solar neutrinos. And I'll start with the atmospheric neutrinos. Particle showers in the atmosphere produce neutrinos. They produce electron neutrinos and muon neutrinos. Kaita-san headed a group of researchers using the Super-Kamiokande Detector deep underground in a zinc mine about 250 kilometers northwest of Tokyo in a study of the atmospheric neutrino flux. They wanted to know how the atmospheric neutrino flux varied as a function of energy and arrival direction. Now, neutrinos arrived at Super-Kamiokande from all directions. They arrive from above, but they also arrive from below. They traverse the entire Earth without interacting. We have heard that neutrinos were very, very elusive. They hardly ever interact. So it's not so surprising that they can traverse the whole Earth and reach Super-Kamiokande from below. Whereas the electron neutrino count in Super-Kamiokande seemed okay, the researchers discovered that muon neutrinos seemed to disappear while traveling to the detector, and the more so, the farther they traveled. Now here's a photograph showing the Super-Kamiokande detector, a huge tank filled with 50,000 tons of ultra-pure water. And I've circled, now I try to see, here we go. I've circled a group of 3 technicians just to show you the proportions of this tank. So there's a huge tank filled with 50,000 tons of water, and the volume of this tank is monitored by about 11,000 optical sensors. And these sensors can detect not the neutrinos themselves, which are invisible, but when they rarely interact with an atom, producing charged particles, electrons and muons. And when these charged particles move through the water, they produce light images, rings like the ring I've shown you here. And so electron and muon neutrinos can be distinguished by means of these rings. Tau neutrinos are generally not detected by Super-Kamiokande. Meanwhile, on the other side of the Earth, in the Ontario province in Canada, there was a detector which was capable of counting all the neutrino flavors. The Sudbury Neutrino Observatory detector was used by a group of scientists headed by Arthur B. MacDonald in a study of solar neutrinos. The photograph shows the Sudbury Neutrino Observatory detector, a sphere 12 meters in diameter, filled with ultra-pure heavy water, 1,000 tons of it. Now, heavy water is just like regular water, except that in each H2O molecule, the hydrogen atom is exchanged for a heavier isotope of hydrogen, deuterium. So whereas hydrogen in its nucleus contains just one proton, deuterium contains a proton and a neutron. And this makes all the difference. When neutrinos collide with deuterium, two reactions are possible. Either on the left hand, the deuterium nucleus is dissociated, or on the right hand, the neutrino is absorbed by the neutron and an electron is produced. So these two reactions can be distinguished, and whereas the left-hand reaction counts all neutrinos independent of flavor, the right reaction counts only electron neutrinos. The sun produces only electron neutrinos. So knowing that, we expect that the count of both the left and the right-hand side reaction should be equal. However, SNO observed that whereas the total neutrino count was as expected, the electron neutrinos seemed to disappear. So we have two observations. And it turns out that these two observations together pick out one single explanation. The neutrinos change flavor while traveling through space. And this means that if we try to determine neutrino flavor as a function of distance or as a function of time, we'll find that this flavor changes. And we are talking in terms of neutrino flavor oscillations. Neutrino flavor oscillations is an effect which, although surprising, is explained by quantum theory. In quantum theory, particles moving through space are described by waves. These waves overlap, they interfere, and this is what we interpret as neutrino oscillations. Quantum theory also tells us that this neutrino metamorphosis is only possible if neutrinos are not massless, as opposed to what we used to believe. Neutrinos must have non-zero mass. The discovery that neutrinos have mass has profound consequences, not only for particle physics, pointing at physics beyond the standard model, but also for astrophysics and for cosmology. The discovery of neutrino oscillations has opened a new, exciting, and challenging field of physics. And all over the world, scientists are picking up this challenge to unveil the true nature of the neutrino. Thank you.
Thank you very much, Olga. We may now have Professor MacDonald with us on the phone, and remember it's around 4 o'clock or so in the morning in Canada. Hello? Do we have Professor MacDonald on the phone?
Yes, hello?
Hello, Professor MacDonald. Good morning again. I'm the guy who woke you up 45 minutes ago.
As it turns out, I did not mind.
Right now, I'm sitting in the beautiful session hall of the Royal Swedish Academy of Sciences here in Stockholm, and we are in the midst of the press conference with many interested journalists from Sweden and abroad, and I'm sure they are eager to ask you questions. Are you ready?
I think so.
Who would like to start? Thomas von Heine.
Thank you. Good morning, Professor. This is Swedish Television, von Heine speaking. Congratulations.
Thank you so much on behalf of myself and also my many collaborators on our experiment.
Neutrinos are very elusive. So you've been chasing something extremely elusive. Was there at any time a moment when you thought, okay, we are really on to something here?
Yes, there certainly was a eureka moment in this experiment when we were able to see that neutrinos appeared to change from one type to the other in traveling from the sun to the Earth. Fortunately, with the availability of heavy water, it became clear, and our statistical accuracy became greater, and we were able to be certain that this was able to be proven with great accuracy. So yes, there was that eureka moment.
Thank you.
Thank you. More questions? Yes, please, in the back.
Okay, I'm from TV4 in Sweden.
Hold on for a second, you'll get the microphone.
I need another microphone. My microphone won't help, will it? Yeah. Okay. I wonder, you discovered that the neutrino has mass, and what is the biggest what is the biggest impact that this discovery has? What will it change?
Well, neutrinos are among the fundamental particles we do not know how to subdivide any further, and therefore their position within the models of physics at the most fundamental level is very important. When you do not know even whether they have mass, it's otherwise difficult to understand how to incorporate them into those theories and give us a more complete understanding of the world of physics at a most fundamental level. Discovering this property therefore helps us tremendously in that regard. They also have significant implications in how the universe has evolved, and knowing whether or not they are massive, whether they change their type, also helps in attempting to unravel those mysteries as well.
But do you know any? Do you know anything that will change? What use? Do you know any practical use?
Well, I guess one could cite the fact that in addition to observing neutrinos as having changed their type, we in particular were observing neutrinos from the core of the sun. And in the process of making our measurements, we were able to verify the understanding of how the processes in the core of the sun, things that have been calculated in detail by people like John McCall, that they were very accurate. Those processes are similar to the processes that these days people are attempting to produce here on Earth in the process of developing fusion power. So in our case, it's held in place by gravity rather than magnetic fields, but knowing that we have a very strong indication that we understand what's happening at a large degree of accuracy in the sun helps us in terms of understanding the physics that leads to the same type of fusion processes in fusion power.
Thank you. Next question, please.
David Keaton from the Associated Press. Professor, congratulations. The question I would like to ask you is, you've spent decades working in laboratories behind closed doors with very few people outside experts that are aware of your research. How did it feel this morning at 4 o'clock in the morning when you received this phone call from Sweden telling you that you had won this prize and that the eyes of the world would be upon you today?
It's a very daunting experience, needless to say. Fortunately, I have many colleagues as well who share this prize with me in the tremendous amount of work that they have done to accomplish this measurement. And so we have a very friendly collaboration among scientists from Canada, the United States, Britain, Portugal, and that group gives me gives me a group of people with whom I can enjoy the moment, at least when I get a chance to talk with them. So there's great camaraderie associated with this work, even though he's spent many years working to try to accomplish it.
Thank you. Do we have more questions? Yes. Maria Gunther, Dagens Nyheter.
Hello, I'm Maria Gunther from Dagens Nyheter. Congratulations to the prize.
Thank you.
I would like to know what more questions about the neutrino you still would like to get the answer to.
Well, there are a number of experiments that are ongoing as a result of these initial measurements by Super-Kamiokande and Snow. In particular, we would like to know what the absolute mass of the neutrino is. We know differences in mass between the three neutrino types. We do not know the mass of the lightest of them that sets the full scale. But there are experiments in which one looks for a rare radioactivity called neutrinoless double slit decay that enables one, if it is observed, to be able to make such a measurement as well as other direct measurements. The fortunate thing is that the development of these underground laboratories that really create in the center of our detectors the lowest radioactivity point that has ever been created, we believe, is also a location where, by eliminating other forms of interfering radioactivity, we are able to make very significant measurements of quantities like neutrinoless double beta decay. Other experiments are looking at whether there are other neutrino types beyond the three that have been clearly observed and are observed to have finite mass. And there is a whole program of neutrino measurements internationally in order to determine their properties and put them within the fundamental laws of physics.
Okay. Thank you very much. Are there more questions for Professor McLaughlin? Yes, Joanna Rose.
My name is Joanna Rose from Forskning och Framsteg. Congratulations to the prize. I wonder, did you have any collaboration with your colleague, the other laureate of the Nobel Prize, Takaaki Kaita?
Actually, as it happens, we were together in Torino, Italy, about 3 weeks ago at a conference. He's a person with whom I have the greatest respect, and also when we first made our measurements, we were able to combine them with measurements that had been made by Super-Kamiokande to give the first possible indication that the neutrinos from the sun also oscillate. And we later were able to go on with our own experiment and take a clear and definitive measurement of that fact. So yes, we have had many communications over the years and have a very positive relationship with the group at the Super-Kamiokande experiment.
Thank you. Are there more questions?
Yes.
Yes, over there.
Hello, Wang Wei from China National Television. I want to ask you some personal questions. What does this honor mean to you, and how will you spend your reward money?
I was told I would be asked that, and I really have not had time to think about that. But what will it mean to me? It means that the work that our collaboration has undertaken and accomplished, starting back in 1984 with our founding spokesman, Herb Chen, who passed away a few years ago from the University of California at Irvine, and George Ewan, who is a very good friend of mine and a professor emeritus here at Queen's University. They, and only 16 of us started, has now come to the point where it has been internationally recognized. We, of course, are very satisfied that we have been able to add to the world's knowledge of physics at a very fundamental level. But of course, this recognition is something that is a tremendous accolade for our group. Thank you.
Thank you.
Okay, thank you. Are there more questions for Professor MacDonald? If not, thank you very much again, Professor MacDonald, and congratulations again, and welcome to Stockholm in December.
Thank you. Stockholm is one of my favorite cities in the world. I will be there with great pleasure. Thank you.
You won our hearts. Thank you very much. Bye-bye.
Bye.
Okay, let's move on to questions to our experts on the panel. Questions? This is your chance. Everything crystal clear, but if there is something you wonder about, some question that hasn't been answered yet, you have your chance now. Yes,
yeah,
come back from Göran Rose.
I wonder if you got in contact with Takaaki Kaita before the conference.
Yes, we did. We spoke to him just after we spoke to Professor MacDonald. We couldn't rig up the phone line, but we have spoken to him, and he was very happy, delighted to receive the Nobel Prize. And he's coming in December. Other questions? Well, then, yes, please.
Thank you very much, Lucia from People's Daily. I want to ask, neutrinos have mass, so I want to know, how do you measure the mass and how much is it? Thank you.
Olga.
So, what we know from the study of neutrino oscillations is that neutrinos have mass, or at least one of the 3 neutrino flavors does have mass. It's very hard to measure the mass itself, and it's one of these outstanding challenges that Professor MacDonald has just been describing. We have been trying to measure neutrino mass for more than 70 years, but the only thing we know is an upper limit on the masses, and the best upper limit comes from cosmology. It's of the order of 0.2 electron volts, which is more than 1 million times lighter than the electron. So that's the only thing I can tell you. The neutrino has a mass, and it's more than 1 million times lighter than the electron. But exactly how much the mass is an outstanding challenge of the field.
Fascinating. Thank you. Was that the last question? If so, thank you for attending. And those of you who have requested interviews with the Nobel Committee members, they will commence immediately after we close their session. But let's close now and welcome back for the announcement of the Nobel Prize in Chemistry tomorrow at 11:45 a.m. Thank you very much.